Hello everyone, Mr. Hasty here. Today we're going to be talking about thermal energy, starting with a few definitions that people oftentimes will use interchangeably but have different specific meanings. And those would be temperature, thermal energy, and heat. So first of all, temperature, we've learned before, is the average kinetic energy of the particles of a substance. So, when we're talking temperature, everything is made up of particles, atoms, molecules, what have you. And those atoms and molecules and everything are always in motion. So, the average of that motion is called the temperature. Okay. Now, the thermal energy is the sum of the kinetic and potential energy of a substance. So, important things to note. If you have more of the substance, you could very well have more thermal energy because there's more motion going on. So there's more than one way to increase thermal energy. Increasing temperature means you're increasing the average kinetic energy, which means thermal energy will go up. Increasing the amount of something will increase thermal energy because if we're summing up the kinetic energy of all the particles, more particles means more kinetic energy and potential energy. So where does heat fit into this? Heat is a transfer of thermal energy. We'll go into that here in a second. But the exchange of thermal energy is called heat. So we've talked about things like a pendulum swinging, and as that pendulum swings, we lose, quote unquote, lose energy due to friction in the form of heat. So what does that mean? So as that moves through the air, it collides with the particles in the air. As it does so, it is creating heat because it is transferring motion from the pendulum to the particles. Now, as those particles move more, their temperature goes up, meaning their average kinetic energy goes up, meaning the thermal energy of the system goes up. So, let's talk about the concepts of thermal conduction and thermal equilibrium. So, thermal conduction is the transfer of thermal energy that occurs when particles collide. That occurs when particles collide. So, as we have two substances, let's say we have a warm surface. So that means that there's a lot of motion in here. Big arrows mean lots of motion. And we have a cold surface. So that'd be less motion. As we bring those two surfaces together, the motion on the right is going to be influenced by the motion on the left. So at first, this is going to have all of its temperature motion, but it is quickly going to start to lose energy as it gives that energy over to the other side. So some of that energy is going to transfer to the other side. As that energy leaves, this side's going to cool down and that side's going to heat up. And as that happens, it'll happen first at the surface and then it'll slowly spread outward from there. At some point, we're going to have the same amount of motion in both regions. And at that point, we say they're at thermal equilibrium. So this is the point at which the thermal energy transfer, thermal energy is TE, is such that they are the same temperature. So, equilibrium is, of course, where they are equal, where the average kinetic energy in each side, the temperature in each side, is the same. All right, so let's talk a little bit about how we measure temperature for a sec. So, when we measure temperature, we typically think of using a thermometer. Now, there's multiple different ways to build a thermometer. Thermometer. The most common understanding of the way thermometers work, the most common experience we have with them is the mercury or alcohol thermometers that basically go up the tube. So what happens there is we have a liquid inside, whether it's the mercury or more commonly now alcohol. As that heats, it expands, and the expansion measures the amount of heat or amount of temperature in that substance. There's also crystal thermometers. Crystal thermometers use color coding to tell the temperature. And basically they have molecules that have different colors based on temperature. And so because they can be very specific, this color means this temperature, they can then be used to monitor temperature as well. So a couple things about this. First, we're going to talk about the temperature scales. We have Fahrenheit, degrees Fahrenheit, which water freezes at. So these are all going to be, we're going to reference them based on the freezing and boiling of water, as well as some other factors. So the first thing to note is that the degrees Celsius is based off the boiling and melting points of water. Kelvin, which we don't say degrees Kelvin, but Kelvin is based off of absolute zero. And Fahrenheit is based off the freezing and boiling of a very specific mixture of water and salt that is a weird basis for how that works. So the boiling point of water is 212 degrees Fahrenheit, 100 degrees Celsius, or 273.15 Kelvin. The freezing point of water is, of course, 32 degrees Fahrenheit, 0 degrees Celsius, and 273. Or sorry, the top one should be 373. This one's 273.15. So you can see that it's still Celsius to Kelvin is really just a matter of that 273.15 difference. And absolute zero is at negative 459.67 degrees Fahrenheit. It's at negative 273.15 degrees Celsius, and it is 0 Kelvin. So let's discuss absolute zero briefly. Absolute zero means the point where all particle motion stops. Now, this is a theoretical place. We have achieved very, very close to that in laboratory settings, but getting to absolute zero is problematic. It's not like a reachable goal. So, a couple notes about this is that there is a low bound, right? You can't go below absolute zero because that means that all, you can't even get to absolute zero, but that means all particle motion is stopped. Also, the upper part of the scale is that there doesn't seem to be an upper bound on temperature. It seems like they can get hotter and hotter. For instance, the core of the sun is 1.5 times 10 to the 7th degrees Celsius. We know that there are things hotter like supernova cores and things like that, but there doesn't seem to be an upward bound that we can theoretically find. There's no like maximum heat that we have. So we're going to finish up our discussion today on the transfer of heat. So the transfer of heat, or transfer of thermal energy, is done through three processes. So the first one is conduction, which we already defined. Conduction is the particle collisions. We most oftentimes think of it in terms of solids, but it can happen in other forms as well. So convection is heating due to temperature differences in fluids. Now, when I say fluids, I mean gases and liquids. So, as you have in a liquid or fluid, let's say the air in your room, if you have hot air lower in the room, it's going to rise up to the top because it is less dense. That's going to force the cooler air to come to the bottom, which, if there's a heating element down there, is going to cause that air to get heated up. This hot air that gets to the top is going to then cool down and start sinking to the bottom as new hot air starts rising to the top. And you get these currents, these flows of the fluid, flows of water, flows of gas that create heat through this process called convection. Finally, we have radiation. It's a transfer of energy by electromagnetic waves. This is how the sun heats the earth. And to get a little bit into the mechanics behind it, is electromagnetic waves are fluctuations of electromagnetic fields, and as they come in contact with matter, they are going to move the charged parts of that matter, the electrons and protons within the atom, and that's going to cause those to move a little bit more. Well, increased movement is increased kinetic energy, which is an increase in temperature. All right, guys, next time we're going to get into some of the math behind this and the concepts of specific heat. So, see you then.